Okay. Okay. Let's take a look at this napkin ring thing. So the way the napkin ring is formed, you all know what a napkin ring is? Okay. No, it's like kind of. It's that. It's a ball. So in math, we distinguish between a sphere and a ball typically. Usually sphere is hollow and ball is not hollow. Usually a ball is kind of like a pool ball, it's solid. And a sphere usually we think of as hollow. So the napkin ring is formed by drilling out the middle of a ball. And that's going to create something called a napkin ring. The numbers are given here. So we're going to start at this solid ball. We're going to drill out a hole of radius 3. And the ball is going to be of radius 6. So we're just taking out the center all the way here. And we want to find the volume of what's left. And this is just a good example to deal with washers because we... Oh, wait. What technique are we using? Shells. Thank you. You could use washers. But we're going to do shells. This is a good example for shells. It gets at some ideas that we are going to see repeatedly throughout the semester, namely solving a circle for either the top half or the bottom half or the right half or the left half. That should be reviewed. If you have the equation of a circle and you're asked to figure out what equation the top semicircle is, or the right semicircle, or the left semicircle, or the lower semicircle, you should be able to do that. So we'll review that here in this problem. So this is going to be the generating region for the napkin ring. If we rotate this region right here all the way around the y-axis, we'll get the napkin ring. We can use symmetry because the top half of the napkin ring and the lower half are the same in volume. So we'll use symmetry. We'll focus on this region in quadrant 1. Okay? So first off, the circle on the outside, this circle right here, is a circle of radius 6, centered at the origin. So its equation is x squared plus y squared equals 36. Circle centered at the origin of radius 6. Okay. We know we're going to use a vertical element because our axis of rotation is over here, and we need to have a vertical element because we want it to be parallel to the axis if we want to create a cylinder. So axis of rotation and the element have to be parallel to create a cylinder. If they're perpendicular, you create a disk or a washer if there's a gap. So cylinder, parallel. And we're going to need to know a couple things about that element. We know that the area of a cylinder is 2 pi times the radius times the height. And when we look at our picture here, the radius is the distance the element is from the axis of rotation. So that's going to be the radius of the cylinder that's formed when we rotate that integration element about y. And the height of the cylinder is whatever that blue distance is. That's going to be the height of the cylinder that we form. So this is the vertical element, typically we would say at x. If you draw a random vertical element, you just put that at a random x. You draw a random horizontal element, you put it at a random y. Okay? So what does that tell us the radius is? 4. So that element moves, right? We have an infinite number of elements always. So each element that we draw that's vertical is going to be a different distance from that axis of rotation, depending on where we draw it. So the radius can't be a fixed number, because if you draw your element here, that's going to be at a different distance from the axis of rotation than that one is. So what is going to be the radius?
Is it 5 minus x?
5 minus x is going to give you this distance. So doesn't x give you this distance right here? This distance right there would be 5 minus x. So what is the radius? Just x. Right? Because that's what x represents. X is representing the distance from the y-axis. I could actually can't leave that up there, actually. Right? That's what x is representing. It's measuring the distance from the y-axis. Well, that's what the radius is. Right? There's our axis of rotation right there. The radius is how far away the element is from the y-axis, which is x. Okay, so now we're at 2 pi x. 2 pi x. And now we have to deal with the height. So here's where we have to think about the circle equation right there. We have to decide what letter to solve for. When we look at this element, it's vertical. Any vertical distance is upper y minus lower y. The lower y is just 0. The lower y is right there. That's y equals 0. The upper y is from this equation, so we have to solve for. I think I heard it. So we're going to solve for y, right? Because we need to write it as a y value. And when we write it as a y value, it's going to look like that. And should we be selecting the positive or the negative for this particular portion of the circle?
Positive.
Positive, because it's above the x-axis. So that's the one that we are going to choose for this particular case. Yeah?
Do you multiply it by 2 right now? Or
We are not going to multiply it by 2 until we set up our integral.
Okay.
Because this distance here is that element length. So that will find the volume of the upper half of the napkin ring. So we will throw in the 2 as soon as we get to the integral part of it, but not yet. So this is going to be the area of the cylinder generated by this element. So then we'll say that the volume, now we'll put in the 2. And it's going to go from 0. This 2 is by symmetry. And I don't know why I said we'll put in a 0 here. The lower piece, the lower curve for this element is 0, but what are the limits of integration? The limits of integration come from the interval where the vertical element lives. So where they?
6.
That's the left endpoint right at 3. The right endpoint is at 6. So we have vertical elements for all those x's between 3 and 6. So it's 3 to 6 because we're integrating with a dx over here. So we know everything in here has to be x's. We know that we're looking at the x interval. And so 3 to 6 will give us everything. And then we have our 2 pi x multiplied by square root of 36 minus x squared. All right, any questions on that setup? Yeah?
I have a question why you're not, like, couldn't we simplify that? 36, square root of 36 minus x squared.
Freshman dream, we wish we could do that. Why can't we do that?
Because it's not multiplication.
Because it's not multiplication.
Oh,
So yeah, that's the freshman dream. You could just distribute the square root symbol. Yeah, but we can't do that. You see why?
yeah.
So if it was 36x squared, you could take the square root of 36 and the square root of x squared. But because if there's a plus or a minus, you cannot. You cannot separate a square root if there's a plus or a minus. So it's one of those algebra things. We'll see a lot this semester, and it will, in a week it'll be totally obvious because you'll have done enough problems. But yeah, that's a very strong inclination to feel like you could simplify that. Okay, so what technique of integration are we going to use here? U sub? U sub. So we're going to choose u to be, usually the standard rule of thumb is inside a square root, up in an exponent, inside an angle. So the obvious choice here is to at least try to see if this works, is to let u be what's inside that square root. And so then we're going to end up with this, negative 2x dx. And when we look up here, we definitely don't see a minus sign, so let's move this minus to the other side. But we do see a 2x dx, don't we? There's a 2, there's an x, there's a dx, right? That matches all that. So we're going to replace the 2x dx with minus du. So it's just a substitution. So let's see. The pi, that's not being used. That's a constant. It can come to the front. Pi can come out in front. Now our integral will not have x limits anymore, so we're going to have to deal with that in a minute. And so in here, the square root of u, so we're going to have u to the 1/2. And then all this yellow stuff, that's negative du. So we'll put a du here, and that minus sign we can put all the way in front. Because, once again, it's a constant. Constants can do whatever you want to do with them, in and out.
Just to make sure, anytime there's a square root inside of the integral, we use u sub.
I wouldn't say anytime. I would say that's the first thing you should consider is u sub. But we're going to see next week that trigonometric substitution works very well if you have square roots. So u sub is a candidate because inside here we see that we have a quadratic, and a quadratic's derivative is linear, and we see a linear multiplier out in front. So that's why we think u sub is a good choice to try, at least. We'll also have other techniques for square roots, but u sub is always the first one you want to try. And whatever you let u be, whether it's in the exponent, whether it's in the angle, whether it's in the square root, its derivative has to be somewhere out in front as a multiplier. And so that's what we see here is that, okay, quadratic derivative is linear. There's a linear function right there. So u sub probably is a good one.
Couldn't you do like 36 raised to the power of 1/2 and then x minus 2, or raised to the power of 2 raised to the power of 1/2?
Can you do that?
I forgot, yeah.
Right. Can't do that. Yeah. You can't split up that square root. Right. Yep.
Would you invert the limits of integration to cancel out the negative?
Yeah.
Okay.
Yeah, absolutely. So we'll see that we can do that in one moment here. So with our u sub, these limits are x limits. We're going to plug them in here to get the corresponding u limits. So when x is 3, you plug in 3 here, you get 9. 36 minus 9 is 27. And then plugging in 6 there, we get 36 minus 36, which is 0. And that integral feels like you're doing it backwards, going from 27 to 0, which of course you can do, right? You just get the antiderivative, plug in 0, plug in 27, take the difference. But you could also say, you know, I prefer to integrate in the more natural order. And if you just reverse the limits of integration, you can take away the minus sign out in front. So that's a pretty good way to do it. Now we're ready to roll. We're going to get 2 pi multiplied by, I'm going to leave a little space. We're going to add 1 to the exponent and get 3/2. Divide by 3/2 means multiply by 2/3. 0 to 27. And that's going to give us 4 pi over 3. Plug in the 27. And let's write it like this for a moment. We'll talk about simplifying it. And like that. So 27 and 3/2. There's a couple ways we can simplify that. Question?
I'm just curious, so right after you've highlighted like the 2 pi and the dx, in the next integral over you have 0 over the 27.
Mm-hmm.
Why is the 0 on top there? Is that because it's negative?
So it's because this is the upper limit. And when you plug in that upper limit here, you're going to get the corresponding upper limit in u. And if we plug in 6 for that x and square, we get 36 minus 36, which is 0. So this is the upper limit here because this upper limit gives you that. And similarly, this is the lower limit here because this lower limit plugged in there is going to give you the 27. So you always have that correspondence. Upper goes to upper, lower goes to lower. That's always going to be our pattern. And then we want to simplify this 3/2 business. So there's 2 ways that we can do it. It's nice if the denominator is a 2, that means a square root. It's nice if this is a perfect square, but it's not. So here are the two ways we could do it. So first off, you are going to see a lot of 3 halves powers this semester. Let's just suppose, I want you to get comfortable with this idea, and that is to write this as 7 root 7. So that should become super obvious. Why should it be super obvious? If we think about what the denominator does, the denominator is a square root. So we were having if we trigger the denominator first, that makes the base a root 7, and then we're going to cube it. And if we cube root 7, that just means root 7 multiplied by root 7 multiplied by root 7. 2 root 7s will cancel out one of the root symbols. So if we have root 7 times root 7 times root 7, that is going to be 7 root 7, because a pair of them turns into a 7. So that we're going to see a lot. There's a lot of the 3 halves powers that just happen to show up when you integrate in this class. So that's one way we could do this. That's, I think, pretty quick, pretty easy. You see that that's going to be 27 times the square root of 27. And then square root of 27. There's a perfect square buried in there. There's a 9 buried in there. So I'm going to combine this stuff out in front first. 27 divided by 3 is 9. So that's going to give me 36 pi for the stuff in front of the root. And then 9 times 3 is going to give us a 3 root 3 for that simplification. So then we'll have 108 square root of 3 times pi. So, of course, the other way you could get at this also is to take the square root of 27 first and write that as 3 root 3, and you'd have 3 root 3 quantity cubed. You could also do it that way, and you'll end up with the same thing. So my tendency will just be to immediately do whatever that base is, that times the square root of it. But you could do it the other way too. Simplify the square root of 27 and then cube it. That will always work.
I'm stuck on the green part of
Yeah.
the top. So like, I see why you choose the u, but then on the du, why is it negative 2?
So what's the derivative of 36?
Oh, it's because we're taking the derivative.
Taking the
of u.
derivative here to get down here.
So the derivative. Oh, yeah. Can you walk through it how you?
Yeah,
want
sure.
to?
So the derivative, we're taking the derivative of this whole quantity. So we have 2 terms. The derivative of the first term is 0 because it's a constant. Derivative of any constant is 0. And then this is a power of x, so we bring the 2 down in front and get negative 2, and then subtract 1 from the exponent. So power rule for derivatives, if we have a power of x, power down, subtract 1. That make sense?
Yep.
Yeah. Other questions on it? Okay, so that is the napkin ring volume. Lots of little algebra sort of buried in this problem, which is why it's a good problem. It gives you practice at some of those things that you need practice at. All right. Our next topic is finding the length of a curve. So let's do a little bit of a refresher from Calc 1 on differentials. So in Calc 1, you had 2 ideas. You had the differential and you had the increment. And we have to be very clear on which is which and what they mean. So let me draw a picture that will probably bring back chills or something. So this is a picture that you saw a lot of times in Calc 1 where you've got a tangent line. I want to draw that a little bit better so that it looks like it's touching in just one place. So you have the tangent line to a curve. Typically, the way you do this thing is you say, okay, I'm going to call that x sub 0. That's a fixed x value where we want the rate of change. And then you add an h over here. This is, right there, that's called delta x. Delta x means the increment in x. That is always a precise number. So it is the exact change in those two x values. Increment always means actual measurement. So the increment in x is that. And when you look up at your curve, we've got a couple of things going on here. So when we come over to x naught plus h, and you draw the vertical part of your differential triangle, you have some stuff here. So this side of the triangle right there, so this is the differential triangle, that triangle right there. It is dx and dy. So this is dx, and dx and delta x are the same, with the independent variable, increment and differential are always the same. Now, when you look over here, this is dy right here, so going from there to there. The differential triangle is on the tangent line. There's dx and dy. Delta y, the increment in y, is that distance. That is delta y. That's the increment. That's the exact y value change between the 2 points on the curve. Right? We have 2 points on the curve, right there and right there. And the delta x and the delta y are the exact differences in x and y along the curve. dy is the difference in the y values along the tangent line. So dy and delta y are not equal. dy approximates delta y. So the independent variable, increment and differential, are the same. The dependent variable, dy and delta y, they're about the same, but they aren't equal. As the 2 points get closer and closer along the curve, the dy and the delta y become more and more indistinguishable, but the dy is used to approximate the actual change in the function. So that is the Calc 1 stuff. Now, we want to measure along a curve, and we have the same model. Delta S, we use S to go along a curve. Some space, I forget, S stands for something in French or something that represents, some sort of displacement. So delta S, same idea. Delta S is the exact change along the curve. Well, we don't have a number line along the curve that if you pick 2 points on the number line along the curve, you could just subtract one from the other. Right? We don't have that. When we have 2 x values, we can do subtraction. 2 y values, we can do subtraction. But we don't have 2 s values along a curve. We don't have a number line taped to our curve. So delta s is going to be that exact change. That's what we want to know. We want to know the distance along the curve. Well, then we can draw this. We can complete. This is an incomplete differential triangle because you never put a hypotenuse on it. The hypotenuse of that triangle is ds. That is the hypotenuse of the differential triangle, ds. And of course, you can look at the picture and you can see that ds is going to give us an approximation for that exact change along the curve. That's an approximation. All right, well, s is going to represent arc length, and it is the integral of ds. Just like x is the integral of dx and y is the integral of dy. The d stands for derivative, and the integral and the derivative undo each other and give you the s, just like it does for x or y. But again, we don't have any clue what these s values are. Right? We don't know those s values. So we need to convert the ds into something we know how to integrate. We know how to integrate functions of x with respect to dx. We know how to integrate functions of y with respect to dy. Right? You're given the function as a function of x or a function of y. Right? You know your function. So this is useless to us because we don't know anything about ds. We don't know anything about the points on the curve. Now, if somebody taped a number line there, yeah, then we could do something about it. We could say, oh yeah, that's going to be s equals 0, and this is s equals 2.2, so then that distance is 2.2. If we knew where the location on the curves were, we could do that, but we don't. So our whole goal is to figure out how to replace the ds with either a dx or a dy. Well, when you look at the differential triangle, it's a right triangle. That's a right triangle. What comes jumping out of your mind when you see a right triangle?
Pythagorean theorem.
Pythagorean theorem, exactly. So we are going to take our Pythagorean theorem and we're going to do some stuff to it. We're going to do some stuff to it. We want to solve for ds. So of course we take the square root, and s is going to represent a positive quantity. So we're going to take the positive square root. We've got that. We're still in trouble though, because that square root, if we plug that inside here, that doesn't make any sense. We need to have a dx or a dy all by itself on the outside, like a factor. And so we need to do some clever algebra here. And the clever algebra that we will do involves the genius concept of multiplying by 1. Right, we do that all the time in math. Multiply by 1. You do it all the time when you're changing units. If you want feet, multiply by 1 so that you get feet in the output. You use that unit conversion all the time. Multiply by 1. So here, the way I'm going to multiply by 1 is dx squared over dx squared. That's 1. Right? So as soon as I do that, that's on the inside of the root here. Now we notice that, oh gosh, there is a dx squared. There is a dx squared. They are a common factor between the two terms in the root. So we're going to factor that dx squared out. That dx squared is coming out through the root, and it comes out through the root as a single dx. Right? The square root of dx squared is going to be dx. We're assuming that dx, dy, and ds are all positive. So what's left in here? Well, if we factor dx squared out of here, we're left with just a 1. And then right here, when we factor out that dx squared is gone. We have dy squared over dx squared, and dy over dx. That's what this is going to simplify to. That's just the derivative. That's y prime. So we're going to get y prime squared on the inside. That we can integrate. Now we have a dx. So if we replace this ds with that expression, that makes sense. We've got a function of x. We can integrate with respect to x. We know how to take the derivative of the function. There's nothing in here that's a mystery. We know how to deal with all those expressions in there. So that is what this is, right there. That's what that is. That's going to give us the arc length from x equals a to x equals b. So now we're dealing with things that we know. So if that's where x is a and that's where x is b, then we're going to get that exact arc along there. So that is how this is going to play out. That's why we're going to get this right here. So that is our new formula right here. This right here is just ds. So the integral of ds gives s, but we have to modify the ds into either a dx or a dy so that we can actually do the mechanics of integration. So let's try one. So here we're going to start with a line segment. Obviously, we could find the length of a line segment just by using Pythagorean theorem or distance formula, but we always start with examples that you could do a different way. And then, of course, we'll get to problems where you couldn't do it a different way. So here's our generic formula. S is equal to that. Integral of ds. And ds is the square root of 1 plus y prime squared dx. So we look at our line here. There's the function. We have to find its derivative. So what is y prime? Negative 3. So we're taking the derivative of the function that generates the curve that we're trying to find the length of. And then we have to plug it in here. So s will be the integral from, they tell us the interval. X is coming from the interval negative 3 to 2. So those are our limits of integration. Those are the x limits of integration. Square root 1 plus Derivative squared is 9. So that's what we have. Square root of 10 is a constant. It comes to the front. So we have that. And what is the integral of dx? Integral of dx is x. That's it. So then we have square root of 10x, negative 3 to 2. Plug in the 2, plug in the negative 3. And we end up with 2 minus 3. So we end up with, that's going to be 5, so that'll be 5 root 10. Ah. There we go. Any step there you want clarification on?
How would we find the limits of integration if they didn't give it to us?
Well, they've got to give us some way to know where we're starting and stopping. Maybe they don't give us the x's, maybe they give us y's, and we have to find x's. Somehow we're going to have to use the original function, or it's going to be given. So maybe they'll say something like in quadrant 1, or somehow they've got to imply where the start point is and where the end point is. I want you to see this integral part. Let's focus on this part for a minute. This, you should be able to go right to here. When you integrate a differential, you always get the length of the interval. Right? If you integrate dx, you get x. That's 2 minus minus. Isn't this the length of the interval? Right? It's 2 minus minus 3. That's the length of the interval. So that's going to be a pattern you're going to see a lot. So in other words, you should be able to cut to the chase on an integral like this. If this is 1 to 10 dx, what's that going to be equal to? 9. Every single time. If you have the integral of a differential, you just do the upper minus the lower. So that doesn't matter if it's y, that's going to be 7. Yeah, so the integral of a differential measures the length of the interval that you're integrating on.
So we won't have to do like the first part, we'll just have to use the formula?
Yeah. Yeah.
So that's just for the independent variable dx equals delta x, and delta x is just
So-
the limits of integration.
Yes, so for either of these, so in this case, let's go back to the prior slide for a minute, because or are we already on we're on the same slide still. So here, the dx and the dy, these are both acting as independent variables here. So here, when you look at those 2 points, the dx and the delta x are equal, and the dy and the delta y are equal, but it's the ds and the delta s. S is acting like the dependent variable here. So x and y are both independent in this context. So here, the differentials and the increments are the same, but there they're different.
Okay.
Because the s is acting, it's depending on x or it's depending on y. You could do either one. So, and we'll do both. Okay, so. But yeah, the bottom line is that this is just a formula that we generated, and it really comes down to knowing the formula. ds is the square root of 1 plus y prime squared. Okay, so. All right, so this book has this kind of fascination with these ones that I refer to as sneaky perfect square trinomials. And on the exam, if I were to give you one of these, I would also give you that hint that it's a sneaky perfect square. And let me show you what I mean by that and show you kind of an efficient way to deal with one of these. It's the last book I used did not have these in them. And the first time I did one of these, I got really tangled up. I was like, man, this is complicated. But it's only complicated if you don't notice what I'm about to show you. So first off, these are our 2 perfect square trinomials. right? That turns into a plus b quantity squared, and that one turns into a minus b quantity squared. So those are the two perfect squares. Those are the two that you know. So here we go. Oh, and notice, what's the only difference? If you look at these two lefts, the only difference is the sign in the middle, right? That's the only thing that's different between those two. It's just a sign. All right. So there's our formula, 1 plus y prime squared. Got to take the square root of 1 plus y prime squared. So usually what I do is kind of try to build up this inside here, one step at a time. Instead of just writing this integral down with the square root of a whole bunch of stuff, I find it easier to start with y prime and then square it and then add 1 and then put it in the square root. Tends to be a little bit easier and neater. So first off, let's take the derivative up here. So that first part is 3 divided by x. Second part is a power thing. Bring down the 2, subtract 1. So we're going to get minus x over 12. So that's our derivative. Now, with these arc length and soon surface area formulas, if you screw up the derivative, you're hosed. Because everything depends on having the correct derivative. So make double sure that your derivative is right. Because if it's not, you're going to be, you could spend a lot of wasted time. If you're coming across something and it doesn't feel like it's working, double check your derivative. The derivative is absolutely essential for this to work out. Okay, now our formula, we have 1 plus y prime squared. So we know that we need to square this derivative. So let's just do it one step at a time. Now here is where I'm going to give you a tip. When you're looking over here, we're squaring this, right? So we're in this scenario right down here, a minus b squared. This is a, and this is b. The minus is not part of b. The minus is in front of b. So that is b and that is a. And what I would do is write it like this. I would be very patient. Just write it like that, a squared. Don't write it as 9 over x squared. That will mess you up. B squared. Okay, b is just x over 12, quantity squared. So just leave it like that. Just be patient. Don't multiply it all out. The middle term, negative 2ab. So negative 2 multiplied by a, which is 3 over x, multiplied by b, which is x over 12. Let me see if I can move that over a little bit. Plus that. All right, so is that okay with everybody? So that's a squared minus 2ab plus b squared, college algebra. So the only thing we want to simplify is the middle term here. Don't do anything with the a squared or the b squared. Just leave those two things alone. And what does that middle term simplify to?
Negative 1/2 x.
Negative 1/2. No x though, because there's an x up top and an x down below. So negative 1/2. Perfect. Everyone agree? And this, if I didn't say that, this is the clue that it's a perfect square trinomial that's in disguise. I'll show you why. Okay, so the next step is to add 1. And we're trying to build up this integrand here. Started with y prime, squared it, now we're going to add 1, and here's where we notice. So y prime quantity squared plus 1, just building up the inside of the root. What's the only thing that changes when we add 1?
Sign.
The sign of the middle, right? The sign of the middle term is the only thing that changed. So we just went from there to there. So that trinomial is in fact a perfect square trinomial. And what it's very tempting to do, if you squared this out, you have 9 over x squared. Here you have x squared over 144. It's very tempting to put it in descending order, take the minus half and put it on the outside, and then you get down here and you add 1, and you would never recognize that it's a perfect square trinomial. Right? If this was multiplied out, 9 over x squared, or do it in descending order. If it was x squared over 144 plus 9 over x squared plus 1/2, who in their right mind would look at that and say, oh, that's a perfect square trinomial, right? You just wouldn't notice it. But it will always be a perfect square trinomial when you add the 1 if this starts at -1/2. And in fact, it's the only way. Right? The only way you can only change this sign when you add 1 is if this middle term were -1/2, because you have to get to +1/2. If you're only going to change that sign, any other number you put there, if you add 1, you are not just going to get -1 times it. And so we ended up with -1 times the middle term. That is a perfect square trinomial, so we know that this just becomes 3 over x plus x over 12 quantity squared. It's a perfect square trinomial. Now, let's come over here. So now we have s is equal to the integral. We have square root of that. 3 over x plus x over 12 quantity squared dx. And our limits of integration, 1 to 6, those are given. And then the square root and the square.
So, sorry, you might
Yeah.
have kind of lost me a little bit. So, I wanted to know where did you get the +1/2, and then what happened to it once you got the perfect or the trinomial.
So this, you know where we get the -1/2?
Yeah.
From simplifying that.
Mhm.
Then we add 1.
Which would give you 3 over 2, right?
No.
No. Oh. Okay.
-1/2 plus 1. So if we have -1/2 and we add 1, -1 over 2 plus 2 over 2 is 1 over 2. So if you have 1 and you take away a half, you're left with a half. So the adding of 1 is what brings us over here to the plus half. And then this is a perfect square trinomial, just like this right here. This is a perfect square trinomial. Right? We started with a minus b, right here, a minus b. And when we squared a minus b, we went to here. That's what this is. So that's right here. Started with a minus b, we squared it, we got to here. We add 1, and the only thing that changed was the sign of the middle term, which means we're still dealing with a perfect square trinomial. It's just that it factors into a plus b instead of a minus b.
Oh, okay.
So now we go back. There's our a right there. And instead of a minus, we use a plus. And there's our b.
Oh, okay. I see what you're using. Okay.
And if you were to check, FOIL this out. If you FOIL this, you get 3 over x squared. You get x over 12 squared. And in the middle term, you get this times 2. The x's cancel. You get 3 over 12, which is a fourth. You times 2, and you get a half. And then you end up with this nice, neat little integral. We can do this. This is 3 natural log of absolute value of x plus x squared over 24. And that goes from 1 to 6. Plug in the 6, and that's going to give us 3 natural log of 6 plus 36 over 24, which is 3/2. And then we're going to subtract off antiderivative at 1, plugging in the value of 1 into this antiderivative. That's 0. Natural log of 1 is 0. And then minus a 24th. Oh, I should not have gotten rid of the common denominator here. Let's leave this as 36 over 24. Let's not simplify it. So then our final answer will be 3 natural log of 6, not 35 over 24. So we'll do a couple more of those perfect square trinomial ones because they're takes a little bit of, it is just algebra. It's just that algebra right there. We start here, we go to here, we add 1 and get to there, and then we undo it. But it's going to take a few of them before it really starts to gel.
Is there something that will kind of clue us in that we're looking at one of these?
Two things. I will tell you.
Okay.
So on the test, I will tell you. And this is your bell right here. If you end up with that, if you have a middle term when you take your derivative and square it, that is the warning bell. Because then when you add 1, you just get the same exact form, except for the middle term is changed in the sign.
Okay, so just look for that.
Yeah, those are the two clues.
Okay.
Yeah. Yeah, so when you're doing homework, you're looking for the negative half.
Okay.
Yeah, that's going to be the clue. Okay, so let's do another of these trinomials because they're tricky. And notice that in this case, everything looks very similar except, oh wait, here we're given a function of y instead of a function of x. So how does the formula change? All right, let's look. So here was the formula we had on the last slide. The only difference, and we normally would just write this as y prime. It's a little less writing to write that as y prime squared. Y and f of x are the same. Y prime and f prime are the same. So instead of a y prime squared, we have an x prime squared. Instead of a dx, we have a dy. So same process. It's just that we have a function of y instead of a function of x. All right, so let's see. And let's look for our warning signs, the warning sign other than the hint right there. So we're going to start with the inside of the square root. So we want x prime. So we start with our function. Instead of y, we have x. Take its derivative. Same process, power rule. Bring down the 4, subtract 1, we get y cubed. And then the derivative here, this is y to the negative 2. So you bring down the negative 2, and you're going to get negative 1/4. Right? So negative 2 is in the numerator. Negative 2 comes down, we get negative 1/4. And then what does the power on the y become?
-1.
Nope.
-3.
Yes. So if we have y to the negative 2 in the numerator, so when we take that derivative, that negative 2 is coming down, and we subtract 1, so it becomes a negative 3. So again, if you blow the derivative, you're going to be in a world of hurt. So double check your derivative. Make sure that you're super careful with your derivative. So that's going to be y cubed in the denominator if we want to get rid of negative exponents. So there's our derivative. Okay. So this is the a minus b thing. So let's write it over here just as a reminder. So I'll just put these perfect squares right here as a reference. Okay. So there's a minus b. Now we have to square it. So perfect square. So x prime squared. We take a and we square it. Again, don't simplify it, just leave it. Minus, so we're right here, minus 2ab. So minus 2, a is this one, b is this one, not including the minus sign, 2ab, plus b squared. So that is how you FOIL. A squared minus 2ab plus b squared. That's FOILing. And again, don't simplify the edges. Just simplify the middle term. And this is where we would know if we're going to have one of these trinomials or not. If we don't get negative half, then square it all out and just keep going. But if you get a negative half, you know something's up. So we're going to just leave this alone. Come in here. Oh, the y cubes cancel. Oh, 2 over 4 is negative 1/2. So now we know for sure that we're dealing with a trinomial. So we started here, then we went here. Now when we add 1, that's going to put us up here. When we add 1, we're going to have x prime quantity squared plus 1. The only thing that changes when we add 1 is that we now have modified the middle term, and all we did was change the sign. Now we have another perfect square trinomial. Now we're up here. Well, it's going to factor into exactly what we started with, except with a plus instead of a minus. So this will be y cubed plus that quantity squared. And that's really easy to take the square root of. So our S will be the integral from 1 to 2. They're giving us our interval. And when we take the square root of that, the square and the square root cancel, so we're going to get the integral of y cubed plus, I'm going to write this with a negative exponent because it's easier to integrate. We'll write it like that. And then we can use the power rule twice, and we'll have it. We'll end up with y to the 4 over 4. Add 1 to the exponent, we get y to the negative 2. Divide by negative 2 is going to give us negative 1/8. That will be from 1 to 2. Plug in the 2. We'll get 16 over 4, which is 4 minus 1 over 32. 2 to the negative 2 is a fourth. And then we subtract off antiderivative at 1, so we're going to subtract off a fourth and add an eighth. And then we just have to deal with all that stuff. The arithmetic. Common denominator is 32. So this one we're going to multiply top and bottom by 32. So that's 128 minus 1. That gets multiplied by 8, so we subtract 8. That gets multiplied by 4, so we add 4. Wherever all that ends up being.
123.
That's what I'm seeing. 123 over 32. Anyone see arithmetic errors or anything goofy? Questions?
Just generally?
Yeah, go for it.
My instinct is to do that arithmetic with my calculator.
Mhm.
Is that something I can rely on being able to do on the exam?
Yeah, because you can have a calculator as long as it's not a graphing calculator, and they all have the change to fraction thing.
Okay.
Yeah, totally fine. Question?
Do you have to see every single step? Or if we like realize it pretty quickly?
You cannot just realize, I think I know where you're going. If you look at that right there, and you look at that right there, you cannot just go from there to there.
No, I was saying like, you took the derivative of x.
Yes.
And the second we simplify that middle term and it's like negative 1/2, could we just go to like 3 lines down basically?
Yeah, you could write that down. That's fine. The one thing I don't want you doing is saying,
Like guessing blindly.
like right here, you see this right here? The antiderivative here? Isn't that exactly where we started except that there's a minus? That you can't just jump from there to there.
Okay.
But yeah, if you come over here, get to the negative 1/2, you can say, oh, now it's a perfect score with the plus. That's still fine. Yeah, that's fine. Yeah, but don't just go from there to there. But this is a checkpoint. If you're dealing with that perfect square trinomial, you know you get the negative 1/2. This and this one and this one should be the same except for a sign. So that's another checkpoint. All right, let's go to one that is not a perfect square, weird thing. So we have another function of y. So we're going to integrate here with respect to y. And there's the graph. They give us the limits of integration. Again, let's just start on the inside. It's just a lot easier to build that thing up on the inside. So we need to figure out x prime. X prime is going to be 3/2 y to the 1/2. So power rule, bring down the 3/2, subtract 1. Now we have to square that. And when we square it, we're going to get 9/4 times y. All right, so definitely not working with that perfect square trinomial case. So we can go ahead and plug that in here. We can add the 1 over in here since we know there's nothing special happening. So we're integrating with respect to y, 0 to 4. And we're going to integrate the square root of 1 plus the derivative squared. Well, there is the derivative squared. And we'll integrate with respect to y. So there we go. And technique of integration, what are you thinking?
U sub.
U sub is a perfect way to go.
Would you combine the 1 and the, oh no, you can't.
You could get a common denominator if you wanted. That's not going to help us, though. You could make this a 4 over 4 and pull out a denominator. That would be possible.
Oh.
You could write it as 4 plus 9y all divided by 4. And then square root of 4 is 2 in the denominator. You could do that. It's not going to speed it up, though. What kind of substitution is this? Linear, quadratic, trigonometric? Not quadratic. What kind of function is this here? In here, the substitution part. So if you were going to use sub, you would let u be whatever's on the inside of the root. What kind of function is that?
Linear mono.
The linear function. And any time we have a linear function, we can cut to the chase using reverse chain rule. Say it louder next time, please. Right? So yeah, if it's linear, this tells us that we can go and use the reverse chain rule. If you write out all the steps of substitution, it's going to work totally fine. But anytime your substitution is linear, it's way faster just to use RCR. So here we have 1 plus 9/4 y. Currently, it's raised to the half. What do? Add 1, divide by the new exponent. So 1/2 becomes 3/2. And dividing by 3/2 gives you a 2/3. Now, how do we do RCR? Well, what is the derivative of the red stuff? What's the derivative in here?
Just negative 9/4.
The derivative is positive 9/4.
Oh,
Positive 9/4, so we divide by 9/4, which is the same as multiplying by 4/9. So here is the RCR part. RCR is going to be multiplied by 4/9. So that part right there is RCR. Right, if you were differentiating this quantity, you would, the derivative of that is just 9/4, so it's not that interesting. So reverse chain rule, if it's linear, you just divide by the derivative of that quantity. So we're going to divide by 9/4, which means multiply by 4/9. And our limits of integration are 0 to 4. So we'll plug in those. So plugging in, let's see, do we have any simplification? Just, it looks like just 8 over 27. So in that antiderivative, first we'll plug in 4. 4 and 4 cancel, so we get 9 plus 1, we get 10 to the 3/2. And then we subtract off antiderivative at 0. We get 1. And then the sort of traditional simplification, we'll leave this 8/27ths out here, and the traditional simplification is just to write it like that. 10 root 10. And then 3/2 is the square root of 10, multiplied by itself 3 times. 2 of them turn into a 10. All right, any step there you want to talk about?
Where do we stop with simplification? Where do you want us to stop?
Stopping with simplification is a little bit hit or miss. Like if you look at the grading guidelines document, I have basic stuff for sure. Perfect squares, definitely simplify. Common factors, definitely simplify or reduce. But you know, like this, if you had this on the exam, I would give you 100% credit right there. Yeah. I mean, this is just what this is typically what we would do. But if you left it like that, I would give you 100%. Yeah. All right, let's take a 10-minute break. I think it's been an hour, right?
Yeah.
I'm still getting used to this time slot. It's a new time slot for us. 3 o'clock. All right.
I fixed it.
You did?
Yeah, it was super easy.
Okay, hold on. Let me hit pause here because I want to. Let's go through another example. Okay, so here is another function of x. So we're going to go back to the first formula we had, function of x. That seems to be the more natural way to represent a function. Seems a little bit easier. Let's take our derivative. So again, we've got our formula here, our generic formula. We want to start on the inside of that root. We need the derivative of the function. We need to square it and add 1, and then take the square root. So let's just start by taking the derivative here. 2/3 multiplied by 3/2, that's 1. We'll end up with x squared plus 1. Subtract 1 from 3/2, we get a half. And then multiply using the chain rule, and we'll have that. So there's our derivative. And when we square this derivative, we'll end up with x squared plus 1 multiplied by 4x squared. So the first factor is a square root, and when the square root is squared, the square root symbol just goes away. And then when we square the 2x, we get 4x squared. So that is our derivative squared. We know we're not dealing with a sneaky trinomial thing. There's no minus half, none of that business. So we can cut to the chase and just go right into our s now. So s is going to be the integral from interval 3 to 9. That's given. And we're going to do 1 plus the derivative squared. So this is going to be the square root of 4x squared multiplied. Let's multiply that out. So that's going to be 4x to the 4 plus 4x squared plus 1 dx. So there is our integrand. Anyone notice anything special about that trinomial? Does it factor nicely? Isn't it a perfect square? That is a perfect square trinomial. La-di-da. Oh boy. Right? That factors into 2x plus 1 quantity squared. 2x squared plus 1. 2x squared plus 1. 2x squared plus 1. So that's a perfect square trinomial. So that factors very nicely. And the square root of the square, they cancel. integrate both those. Let's come over here. So we integrate, we'll get 2/3 x cubed plus x from 3 to 9. Plug in the 3, or plug in the 9 first, plug in the upper limit first. And let's see, I'm going to write this. So that's 9 cubed. There's a 3 in the denominator that's going to wipe out one of the factors of 3 in the numerator. So I'm going to write it this way. I'm going to write it as 2 times 81. That's 2 of the 9s. And then the third 9, I'm going to cancel a 3 with it. So it's going to be 2 times 81 times 3 plus 9 minus. Plugging in the 3 here, we get 3 3s. One of them cancels, so we'll get 18 minus 18 minus 3. So that'll be the arithmetic part of it. And whatever that all simplifies to, Dan, did you get a number?
I got 46 plus 9.
So 54?
495.
495 total?
Oh, no. I'm still working my way through. I'm
Oh,
sorry, I
okay.
don't have the final answer.
Did somebody add all that up yet? Or am I going to have minus 9, minus...
474?
Say again?
474?
474? Somebody confirm? The hard part. Doing the arithmetic.
Yep.
474. All right, so that is our arc length. Any step that's bothering you? Take a roll. Any step bothering you? That one's not too bad, I guess. All right, well, here's another perfect square trinomial that's sneaky. So you all start working on this one while I take a roll. Use one of those other ones that we did already as a model. I believe in you. It's sneaky, but that's okay. And Jill here. Logan here. Alex here. Araceli. So enthusiastic. Dan D here. David here. Dan Ha? How is it said?
Huh? It is hot. You know.
Ha.
Yeah. Dan
Dan Ha?
Dan Pitt. Like Army.
Dan Ha. Yeah, not Ha. I don't know how to even indicate that enunciation on an A.
Like H-U-H.
Oh, Ha.
Yeah. Dan.
Apparently there's two ways of spelling it. They
Like
spell
if
it
you got
really-
punched in the stomach.
Okay, all right. I will never forget.
They literally spell it so.
Okay, James is not here. I think. Oh, you are here. And you were here last time. But you weren't here the time before.
We're waiting for that.
You were?
He does it on the
You were here.
I was here, then I was there, now I'm back here again.
Okay.
Derivative.
I trust you. Ryan Jones, he is sick.
And then we did
Ian.
cube it of the whole. I mean, we split it.
Ian Joseph.
Oh, because we're going.
Joshua. Joshua. I think you came in right after the roll last time. Jordan.
What is that then?
Gerardo.
Huh?
What?
A to B.
Friedrich.
The square root.
John.
Here. 1 versus JP. What is it? Y.
Oh, gosh.
What do you get for the derivatives? You get the x to the third minus 1/4 x negative 2/3.
Really? You don't really have one.
So you take the derivative of that first.
Yeah.
Is that like right?
Technically, kind of.
Kind of my middle name.
Yes, that is the equation that we use.
Hannah.
So now we filled it out. Not
Y prime is
Dustin?
what I got was
Hello.
X.
Oh, yeah.
X to the power of the third.
Adriana?
Everything vortex.
Hello, hello.
Is a minus two.
Riley? Riley and Dante's here. Caesar's here. Cole? Nicole? Roberto here. Sim is not here.
That's what I got. I don't know.
X to the 2/3.
Eliana?
1/3.
That's what I got.
Celeste is usually back there?
No.
Eliana's back there. Oh, you're Celeste. Yeah, you're Celeste. Eliana's usually back there. But she vanished. She okay? She's fine.
She's not here, so she's probably at
She's
home.
fine.
You square it. Not yet.
She's not on I-70?
Not yet.
Once we get Y prime. Yeah, that's what it is.
Are you thinking about the hearse? Yeah, I'm still thinking about
Did
it.
you get X to the 2/3?
Oh, hopefully the body was okay.
What did you get?
Well, you first gotta add one to it.
Down 1 square.
Oh, wait, no, you're right.
I'll start. I'm sure you guys are doing it totally fine.
Sorry.
Everyone get that for their derivative?
Yeah.
Or at least most of you?
Square.
Hopefully all of you.
AB.
Question.
Yes.
When you did the derivative on the second one,
Yes.
wouldn't it, when you bring down the 1/3, is it not 3/4 times 1?
So it's 3/4 times 1/3 and the 3's cancel. 3 over 4 times 1 over 3, so we have a 3 up top and down below.
Yeah, I just put as 3/12. That's the same.
Yeah, same thing. Yep. So then a squared minus, does everybody agree that we get half in the middle? Minus half?
No.
Do you see it? X to the 2/3 times x to the minus 2/3 is x to the 0. X to the 0 is 1. And then we have 1/4, and you double to get to the middle. So 1/4 doubled is 1/2. So then plus 1/4 x to the minus 2/3 squared. Okay, question?
Sorry, could you run that back a little bit? You got negative 1/2 because.
A times b times negative 2.
Oh, because
So
those two
a
are
times
not-
b times, so negative 2ab. So there's a times b. So the x to the 2/3 and x to the minus 2/3 cancel.
Yeah.
And then 1/4 times 2 is 2 over 4, which is a half. Half.
You know what I mean?
That, lo and behold, is another perfect square trinomial. Very mysterious. Oh, wait, not yet. We have to add 1.
Do these cancel each other out with A and B?
We have to add 1.
It's gonna be the X to the 2/3.
Because when you do an equation, there's A squared minus 2AB plus B squared, right?
Okay, so there we add 1. And we notice that the only change was the half thing. So that is going to factor into x to the 2/3 plus 1/4 x to the minus 2/3 quantity squared. Question?
Wouldn't that be negative 1/4? On the,
Here?
no, on top?
Here?
Yeah.
No. Because b does not include the minus.
Oh, you're right.
So when you, and you can think of it this way, when you square this over here, if you were to square the minus, it would go away. So yeah, you don't want to include the minus.
Where does the negative 1/2 come from again?
Negative 1/2. So the middle term up here is minus 2ab. So a times b is going to be 1/4. And then you double 1/4 to get 1/2. Everyone follow that? Make sense to get the negative half. And then add 1, it turns to a positive 1/2. That just modifies the perfect square trinomial, but it's still a perfect square trinomial. It's just a plus b squared instead of a minus b squared. And now we can do s. So the arc length is s. That's going to be the integral from 1 to 8 of that squared. Or, excuse me, of that square rooted. And if we take the square root of that, we get x to the 2/3 plus
You would be adding.
1/4 x to the minus 2/3 dx.
Right? The original function.
So when we integrate, we're going to add 1, get x to the 5/3, divide by 5/3, which means multiply by 3/5. And then over here, when we add 1, we're going to get x to the 1/3. Dividing by 1/3 is the same thing as multiplying by 3. And that's from 1 to 8. And plugging in the upper limit, we have a perfect cube. So the cubed root of 8 is 2. 2 to the fifth is 32. So we're going to have 3/5 times 32. Plugging in the 8 here, again, perfect cube, so we get 2. We're going to get 6/4. Well, I guess we just write that as 3/2. Plugging in the 1, we're going to have minus 3/5 and minus 3/4. Common denominator of 20? So, yeah, whatever that all simplifies to. Ooh.
Just square root.
That's going to be 12 times
I just
32
boxed it there, it's fine.
plus 30 minus 12 minus 15. Somebody has the final fraction. Tell us.
387 over 20.
387 over 20, thank you.
You know what it is?
I trust you.
32 times 10 times
That's what I got.
Oh, good.
Yep.
We have
10
confirmation.
is 320.
Confirmation, good. 3 times. It's got to be right.
And that's 30.
No way 3 of us made a mistake. No possible way. Never happens. No one ever strikes out. All right, so that is perfect square trinomial case. We have one more example in this section, and that is using technology. As you can kind of see, these functions have to be really cooked up for this to work. You have to get a minus 1/2 in the middle term, or you have to end up with something that you can take the square root of, like a perfect square trinomial. Most of the time out in practice, you're going to come up with a function that's not going to be easily integrable. So we want to know how to do it with technology also. So let's take a look at these two examples. So with this one, we're going to take our derivative, and we're going to square it. We get 4x squared. And when we come over to plug it into our formula, we have an integral from -1 to 1. And we have this function that is not integrable at this stage of the game. That is an integrand that we will learn how to integrate once we get to trigonometric substitution. But at this stage, we can't integrate it. And so one of your jobs at this stage is sort of noticing when you can and can't integrate something. And it's a very fine line. If we put an x out here, then it's integrable. Then you could let u be 4x squared plus 1, take the derivative, and you could make it work. So it's very in a lot of cases, it's a very fine line between something that you can integrate and something that you can't. But this does have a pattern to it. It's a sum of two squares in here, and that's a type of pattern that we'll be able to do with trigonometric substitution. Sums of squares and differences of squares. But at this point, we don't have it. So you can use whatever graphing calculator, I mean, almost all the calculators have some sort of integration option. Desmos is a really easy thing to, if you're trying to evaluate and get an approximation, Desmos works great. Desmos works great anytime you want to confirm anything. You know, if you're getting a final answer, you can always type it into Desmos and check and see if you are on the right track. So one thing that I was talking to somebody the other day about, with the worksheets that you're going to turn in, if there's lots of equation editors. If you don't want to handwrite, you want to try to use an equation editor, you can use the one in Word, you can use the one in D2L, which is not great. Desmos is an equation editor, essentially. You can type in whatever you want in there. And I've seen people, if there's 4 steps, you can just type 4 different steps and then copy and paste it. There's lots of ways you can use equation editors to do your worksheet if you want. So here for us, we just type INT. What were our limits of integration? 1 and 8? Or something else? -1 and 1?
Yeah.
-1 and 1, okay.
Our worksheets are due at the same time as the rest of the homework.
Yeah, same exact, yep, midnight of the night.
There's a little thing that says your name on the side of the
You just upload the worksheets or answers to the worksheets on OneNote, right?
handout.
Yeah, I think there are problems that are.
You're gonna have to show it.
Just like finding the
You're gonna have
area.
to show you. It's actually pretty easy to get into.
So,
Click on your name.
so that's all you do. Pretty simple, right? Wow. It's amazing. Technology these days. Back when I was in school. All right, so there is our approximation right there. Make sense? Okay, I heard somebody asking about the OneNote worksheets. Just remember that those worksheets are right in OneNote, and you should see your name. And if you open that up and click on worksheets, there's the first one for chapter 6 is right there. So again, you can write if you have a tablet device. You can do whatever you need to do. You can separate, make that more space if you need to. Doesn't matter. You can take photos and insert photos really easily if you want to do it on paper and then just put in the photos, the images, whatever you want to do is pretty simple.
Do same day as the homework, right?
Do same day as the homework. So if we come back up here to welcome and we look, our homework is going to be due Sunday night, so our exam is on the 13th, so 2 days prior, so the 11th is when it's due by midnight. Sunday the 11th by midnight. What was that question?
So the OneNote should be on Teams.
Is-
And then you can send you an email.
Dan, huh?
Well, Sunday would be one
Are
day.
you asking a question?
No.
Okay. So, what was that?
Wouldn't Sunday be one day before because we have class?
Oh, I'm sorry. Yeah, it would be the 10th. 10th? No,
I
12th.
said the 12th.
12th.
So it's one day before.
It's one day before. Because we meet on Monday. I was thinking my other class is Tuesday, so it's different. Yeah, one day before. So it's the 12th. It's the 12th.
Is for your other class though on Sunday too?
Yeah, it's 2 days before. Well, their tests are on Thursday, so their
Oh.
homework is due on Tuesday night. So it's 2 days. It is 2 days before, actually. You guys have it better. It's only one day before.
Yeah.
You get one extra day. And you guys have it lucky. Yeah, you might want to think about this, Dan. Because you get your test on a Monday, so you have that whole weekend to study for it. Those guys have to take it on Thursday.
That whole weekend.
Don't do that.
Yeah.
Don't do that. Don't do
Very
that.
smart
I've done that
idea
before.
I know. We all have. But we've all learned that lesson the hard way.
there. The hard way.
but we still do it sometimes. But not this semester. This is such a unique semester. Okay, so let's do one more of these with a technology derivative, and we're going to square it. And when we square this derivative, we FOIL. So 16 minus 16x plus 4x squared. And so the integral is 0 to 4 square root. When we add 1 to this, we'll have that. And that is definitely not integrable. So we'll just type it right into Desmos or your friendly phone calculator or wherever. And we will get our approximation. All right, any questions on that stuff?
Will we ever run into the technology-assisted ones on an exam?
Not on the exam, no. Yeah, that just pops up in homework and stuff. It's helpful to know how to do integrals with technology. All right, we ready for surface area?
Yep.
Kind of bored in 2 dimensions. Time to jump again. Quantum leap into one more dimension. Quantum leap into one more dimension. We'll go here. Jump in dimensions. Okay, so we are going to deal with surface area, but only for very nice surfaces. We are going to generate these surfaces by rotating a curve around an axis. So kind of like a solid revolution, except we're only going to rotate, we're only looking at the outside. We're not looking at the volume. So the idea is that we've got a curve, rotate it around, we get this surface, we want to find the volume of that surface. Anytime we're finding volume, did I say volume of the surface? We want the area of that surface. Anytime we're finding area or volume in 3 dimensions, or even area in 2 dimensions, we come up with approximating geometric shapes. So your first thing was rectangles for area under a curve. When we were doing volumes, we did disks, we did washers, we did shells. So some sort of geometric object that can give you a good approximation. For a surface in 3 space where it's generated by revolution, what we are going to imagine is that if you take a cross section and then you add a little thickness to it, it's going to look pretty close to a base of a cone. You can imagine all of these kind of as cone bases. They call them frustums. So if you take the frustum of a cone, it's sort of a little tilted ring. You can imagine that those are decent approximations along the curve, along the surface. And standard Riemann sum stuff. As the number of frustums increases and they get narrower and narrower, the approximation gets better and better. And we take the limit of the Riemann sum. We get the exact area. So first off, the area of a frustum is pi times the big radius plus the little radius times the slant height. You do not need to know that. Okay? But that is what the area of a frustum is. Think about as that frustum gets flatter and flatter, don't these 2 radii become indistinguishable? Right, as it gets flatter and flatter, the R1 and the R2 are approaching each other. And so what we are going to see when we go with the Riemann sum is that our area is going to be approximated by this. This is going to be the approximation for the area of one of those little, kind of just a thin little, whatever we want to call it, cross-section. It's really a slice because it has thickness, but doesn't feel like calling it a slice makes sense. So very thin frustum, that's going to be the area. So you can imagine, so this R right here, they become the same, so that's where the 2R comes from. So we have 2R times pi times ds. ds is going to be the slant height. So ds is the slant height. Which we looked at a few minutes ago when we were doing arc length. ds, right? ds is along the curve. And what is 2 pi r? Circumference of a circle. So here's conceptually what we're thinking. We are thinking if we've got a surface of revolution, if we can find the circumference and then multiply by ds, that gives us a little thin frustum. So the circumference and then multiply by ds, that gives us a frustum. And when we take the limit, then we get the definite integral. So this right here is the area of a thin frustum, and it's basically circumference by slant height. So when we're doing surface area, we think about circumference times ds, and you already know how to get rid of ds. This is what we did already today. We've got the ds, and we're going to rewrite it in terms of dx so that we can integrate, because we know all about x. So when we look at the limit of the Riemann sum, again, up here, we know nothing about s. We've got to replace the ds. We replace the ds with the arc length formula, and that gives us the surface area formula. So the only thing, so I said it's 2 pi r ds. R is the function, right? The function is measuring how far away you are from the axis of rotation. So that is going to be the radius. So the function is the radius right there. So it's 2 pi r ds. So let's try one. 2 pi r ds. Yeah, so you think of this whole thing as a very thin frustum. 2 pi r ds, thin frustum. Thinking about frustums. Okay, so here is our curve. We don't have to graph it. With arc length, it's really just a straight up computation. The visual is not going to help us a lot. But if you want to think about it, it's just a square root function. So you're thinking about somewhere in quadrant 1, it's some sort of arc like the bird wing thing. It's just in quadrant 1. But it becomes very mechanical for arc length. We know we need to replace the ds with a dx or possibly a dy thing. So we have to go ahead and go through the derivative process. So we're going to take the derivative. So we bring down the half, subtract 1, and then we know we're going to have to square it. So I would just sort of do this on the side. And then we know we're going to have to add 1 to that. So our surface area, we'll use a capital S to represent surface area. So it's the integral of 2 pi times the radius, and the radius is the function. If you're visualizing this function, something like that, right, this distance right here is the radius. That's given by the function. If we're rotating around the x-axis, the function tells us how far we are from the x-axis. So the radius is the function. And then the ds, that's the slant height, 1 plus y prime squared. So we have 16 over x plus 1. And now we have a dx. And this is going to go from 9 to 20. So there's our setup. Yeah?
Why is it not 16 over x squared?
Because when we square this, this is the square root of x, and when it gets squared, it becomes just x. So this we can write as 4 divided by root x. And then when we square it, we'll get 16 over x. So this is just like what we did a minute ago. There's the ds. The only difference is you put a 2 pi r in front. You put a circumference in front. So 2 pi r gives us a circumference. ds is our slant height. We integrate from 9 to 20. We will get the surface area. Okay, so now we have some algebra. 16 pi is coming to the front. Let's get it out of the way. And then we have 2 square roots. Let's remember back from algebra, if you have a product of square roots, all you do is multiply the insides together. So we're going to turn them into one square root where the insides are combined. And to combine these insides, really all we're doing is distributing the x. So this becomes 16 plus x on the inside. Everyone see that? So the inside of the first square root gets shared with the inside of the second square root. So this x right here has to multiply by this, and it has to multiply by that. So we're distributing it to each term inside the second root. And so the x cancels with the denominator when it multiplies by the first term, and then x. That we can integrate. That's just a power rule thing. So this will give us 16 pi, and then our base is 16 plus x. In the integrand, it's to the half. We add 1, we get 3 halves. Dividing by 3 halves means multiplying by 2/3. I didn't leave space in front. And what would one other step be? Let's just suppose just for a moment, if this happened to have a 5 in front, what would be the one next step?
Reverse chain rule.
Reverse chain rule, we'd have to divide by 5. But in this case, it's just a 1x in there. So divide by 1 doesn't change anything. So because that's linear, right? 16 plus x is linear. So if there was a coefficient of x that was other than 1, we'd have to divide by it.
How come that just became x instead of square root of x?
So the square root property says if you have two square roots, let's just suppose we had something like this. You combine the insides. So this is going to be 8 plus 2x. So we're multiplying this by each of these. One square root. So it turns into one square root, and we take x and multiply it by this, which gives 16, and we take x and multiply it by that.
Okay.
So it's the insides that we're combining into one square root. So one root to rule them all. All right, one root only. And then 9 to 20, limits of integration. So the constants we can combine, so we have 32 pi over 3. Plug in the 20. 20 plus 16 is 36. That's a perfect square, so we get 6 cubed, which is 216. Plug in the 9. That's 25. Square root of 25 is 5. 5 cubed is 125. And that will be our final answer. We have to do a little bit of multiplication. So 32 pi over 3 multiplied by 341.
10,912.
And so say that again.
10,912.
Thank you. Times pi divided by 3.
Yeah.
Yep, and that's not divisible by 3. So yeah, we'll leave it like that. Thank you.
Why do we have addition 216 plus 125? Shouldn't that be subtraction?
That's a great point.
That's what I was.
Okay, yeah. That number seems so big. There is the mistake right there. Thank you. Everyone notice that? Plugging in the 20, we always subtract off. Or we should be subtracting there. All right, so slight modification here. That will be a little bit less. That will be a little bit less. What is that?
I get 91.
91 in here?
Yeah.
91 in there. That's not divisible by 3. So then 91 times 32 is?
2,912.
2,912. 2912. Thank you. Subtraction. Subtraction. It's getting late. Okay, so any questions on any step there? Really similar to arc length. Only difference is that we have a 2 pi r out in front. So let's try another one. All right. So we know that we have a ds. We know that to deal with ds, we have to have a 1 plus derivative squared. So let's go ahead, and that's just a good way to start, is to find your derivative, square it, and then start plugging in. So the derivative here, we're going to bring the half down in front. We're going to have 4x plus 6 to the minus 1/2. And then we have to multiply by the derivative. How does that look to everybody? Seems plausible. Then we have to square this. Can we square that? So I think we're going to end up, bless you, I think we're going to end up with that. Stare at that for a moment and tell me if you agree. So we have a 4 in the numerator, a 2 in the denominator. That simplifies to a 2 up top. Then we square it and get a 4 up top. This thing is a square root in the denominator. So when we so doesn't that square root go away?
Yeah.
Well, so that should be gone. Doesn't want to leave. So just that. Yeah, just that. Because when we square this, the square root goes away. So we're just going to have 4x plus 6 to the negative 1, which is 1 over 4x plus 6. Okay, I agree with that. So now let's toss it into the formula. So the surface area, big S, is going to be the integral 2 pi r. So 2 pi r. R is the function. The function tells us how far away the axis is. So there's 2 pi r. And now ds is the square root of 1 plus the derivative squared. So 1 plus the derivative squared, we just found the derivative squared to be that. dx. Okay. So we're very similar to where we were before. We have 2 square roots. We have to combine the insides of the 2 square roots. So here's how I would like you to think about it. Think about distributing that 4x plus 6 to both the 1 and to the second fraction. If you think about it that way, it's going to simplify a little bit easier. Like, you don't want to FOIL there. You want to take that whole 4x plus 6 and send it to each term in that second root. So here's what we'll end up dealing with. And tell me if this makes sense. So we have 1 square root. So the 2 square roots combined into 1 square root. And then 4x plus 6 times 1 is 4x plus 6. And isn't 4x plus 6 multiplied by the second fraction just the numerator? Because it's going to wipe out the denominator. So we'll have that. So this will be, let's simplify the inside here and then we'll do the integral. So we've seen quite a bit of these root integrals today. So the inside of that square root is in fact linear. So we're just going to do the regular power rule thing, but then do an RCR at the end. So this is going to be 2 pi multiplied by, I'll leave space this time. So the 4x plus 10 is raised to the half power, so it goes up to the 3/2. Dividing by 3/2 is multiplying by 2/3. But then what do we do with the RCR part? Divide by
4.
4, exactly. And that was 0 to 5. Yeah.
And just to clarify,
Yes.
on top of all of those, when they're multiplying again, you just, what is it called?
Distribute.
You distribute it, right?
Yep, so this gets distributed to each term in the second square root. That's right.
Or foiled.
If you FOIL it, though, then you're going to break it apart and not have a common denominator, because you do 4x times this, 4x times that, 6 times this, 6 times that.
Oh, I see.
So the idea is that if you have
You did the
something,
whole thing.
yeah, you can do this kind of thing. You can say, okay, well, let's distribute the a plus b to the c, and then let's distribute the a plus b to the d. That's legit. All right, let's simplify here. So it looks like pi by 3. And then plugging in 5 gives 30 to the 3 halves. Minus 10 to the 3 halves. Which you could, on an exam, I'd be totally fine with that. This would be the more traditional way to simplify it. And then we start getting to, Dan mentioned earlier, when do you stop? Because you could still then factor out the 10 root 10, like you could keep going for some, 10 root 10 is common to both of these, so you could factor out the 10 root 10. So that's probably considered the simplest, but totally fine to have left it up here in that one. All right, you ready to try one? I'm ready to watch you try one. Unless someone has a question on any step here, any of the algebra. Is your algebra coming back, Dustin?
Would we get these formulas like on a test, or should we like have these memorized?
These you should have memorized. There's not going to be a ton of formulas. We've almost covered all the formulas that we're going to have, other than the stuff in the application section. But yeah, you need to know the formulas for an exam, like a chapter exam. But on the final, you get notes.
So like on an exam, we might just see that line with 16
Yes.
and all that,
Yeah.
and we'd have to know those.
You'd have to know the surface area formula, yeah.
Okay.
Yeah.
But would you say like use the surface area formula to?
Yes.
Oh, okay.
Yeah, yeah. And you can look at 3 prior exams, yeah. It'll say find the surface area of. Okay, let's. All right, you guys try this one. I drew a picture for you. It's so much for you. So much for you. Picture, colors, formula. All right, give it a shot. See if you can get it.
It might just be crazy. I think let me ask.
Yeah, question.
Yeah, no. Yeah, shouldn't that be 20? Or am I just going crazy?
Which part?
The 5 times 4 is 20,
But if you had 10, 5.
Oh, yeah.
Give some flexible.
20 plus 10.
20 plus 10.
Yeah.
Don't need a calculator for 20 plus 10.
Hopefully.
Plus 20 plus 10.
Matters to assume.
I assume you all were cashiers at some point. You can do 20 plus 10.
That's a very hard problem to solve.
Tough math.
Tough math indeed.
Chain rule. Don't forget the chain rule when you do your derivative.
We're doing number 18.
For that first one.
Yes, right. When you differentiate this, the base is 5x minus x squared. So the chain rule piece would say multiply by the derivative of the base.
So it's not like this.
So now you have to. So So the half is going to come down.
Yeah.
The base is going to stay the same, and you subtract 1. You don't change both the base, right, at the same moment. When you're doing the power rule part,
And then I would multiply.
and then you multiply by the quantity, that quantity.
Yeah.
Yeah. Chain rule. Yes, it's in the right direction. The derivative of this, though, is 5 minus. Not it. What's the derivative of that? Derivative of x squared is 2x. Everyone okay on chain rule? You dying on chain rule? Let's see. Did he get a different derivative? That. Perfect. That looks good. And now, can she square it? Can she square it? Derivative okay? Oh, man. That looks great. Does love it? Yeah, that's right. That's right. Yeah, that's right. Squared. Yep. Looking good.
Oh, the squaring is going to be so annoying.
Does it look nasty? So that
Well, that's simplified.
is that a what is that there?
5
So that derivative is 5 minus 2x.
minus 2x.
Right, the derivative of the inside is 5 minus 2x. So this should be a 5 minus 2x out here. Do you agree? Okay, he agrees. A reluctant agree.
Yeah.
So when you're squaring it, this 2's in the denominator, so it's going to be 4. The square root will go away there. And then that thing will be squared.
Oh, okay.
I distributed it.
Yeah.
That came down, that, and you squared. Yeah, that's it. Yeah. Lo and behold. What's going on here?
I'm just slow.
So, let's see, something is up here at this stage. So you brought down your half. So you subtracted 1, so you got a negative 1/2, so that popped downstairs, that's all perfect. But the numerator is going to be the derivative of the entire inside. So the derivative of this term, I agree, is 5x, but what about the derivative of the second term? Yeah, that's going to be. Yes, that hurts. Good?
This is quantity, square root.
Yeah, there we go. Yep. Now you
The derivative?
square.
Yeah.
Square it and add 1.
So it's like 1/2 and then the inside. So negative 1/2
This is a square
times
root.
5 times 2x.
Yeah, so if I square root, it'd be
Or no.
That's not what you
use negative 2x times
Yeah,
negative 2x.
oh, okay.
the quantity 5 minus 6. Like that's good. That's good. So the 1/2 comes down. This stays the same, and you subtract 1. So yeah, you have that, and now you've got to square that thing. And this half, oh yeah, you could do that. That's really fine. You could distribute this half to here. And then you just have to square that. That is looking...
I don't think I got it right
When you squared it? Let's see, so
X squared.
Wait, why is
squaring that,
Is it factor?
4, this, the square root goes away.
My,
And squaring this should be FOIL.
That's what yeah, because at first I just had them individually.
Right, yeah, so you can't square each individual, you've got to do the whole FOIL thing there. Although you might not want to foil it yet. You might want to just wait and see if
Right.
it write it as 5 minus 2x squared and see if it does anything. All right, I'll start writing the first two steps down here.
I don't know. It's division of
I'm speaking like me.
I don't know.
Yeah, it's essentially it comes out to this, so you should include this one.
Yeah, I mean, okay, fine. Whatever. Yeah, yeah. I was like worried on the bottom. If that's it. Then
I think the bottom one you said was right.
Okay. Then you foiled it.
So that is what you should get for the square of y prime. And you can definitely foil out that numerator. I'm just going to wait a moment and see what happens. We've seen that with these surface areas, we always end up with 2 square roots. So let's just wait for a moment and see what happens when we put everything together. So our surface area is going to be 2 pi multiplied by the integral from 1 to 4. And then r is the function. So there's the function, 5x minus x squared inside a square root. And that's going to get multiplied by the square root of 1 plus all this. So, and now I'm seeing that it probably is going to be important to FOIL out that numerator. You know, I thought maybe there might be something else, like a 5 minus 2x in the denominator somehow, but there isn't. So let's FOIL that. So that's 25 minus 20x plus 4x squared.
Why? I'm saying I factored that too. You didn't factor it in?
Yeah, yeah.
And then you just squared the two, I think. Yeah, that's fine. So we know.
Okay, so there's the setup of our nasty surface area integral.
Yeah, we got it right.
Yahoo!
It just looks so messy.
I know, it is. It's really, really bad. But when we watch this, though, what we notice is that this inside of the function there, the inside of the root, that's going to cancel with the second denominator. So that's really going to simplify things a lot. So we end up with s equals 2 pi integral, 1 to 4. So one big square root, 5x minus x squared is going to be multiplied by 1 first. And when we multiply it by 1, we just get 5x minus x squared. When we multiply it by the second part, so I multiplied it by this, now I'm multiplying it by that, it cancels with the big chunk of the denominator. And it's going to leave us plus. So in the numerator, I'm going to rewrite that so it's in descending order. Don't have to, but that tends to be how we like it. And that's all divided by 4 times dx. And that 4 is inside the root. Maybe I'll just move it up a little bit to make sure it's inside the square root. Doesn't look like it's outside. So any algebra issues up to that point? Roberto?
Actually, if you go up real quick, I had a question on the y squared, the y prime squared.
Mm-hmm.
Because wouldn't that be 3 over 2, right? If you square, if you square the y prime.
Square the y prime, we're going to square each part. So I'm going to square the 1/2 and get a 1/4. This is a square root, so when it gets squared, the square root goes away, but it's in the denominator. And then that squared is the numerator.
Oh, okay. That's what you're saying.
You see it?
Yeah.
Dustin?
In that same point, basically, I distributed that 1/2 in.
Mm-hmm. Over to here.
Yeah, before I squared it.
Yep.
Like it should end up the same.
That'll be totally fine.
Okay.
Yep, that's 100%. So here we've got to somehow combine everything on the inside. Here's going to be my strategy. I'm going to take this part and multiply it by 4 over 4. So that we can clear. If you want, you could just, oh, you know what we could also do, actually that looks even simpler now that I'm staring at it for more than a minute, is you could distribute this in really easily, and then it's going to look a lot like what you just described.
Okay.
So let's divide that 4 in, because there are the first two terms are divisible by 4, so The terms that have an x in them we'll be able to combine them. So that's going to be plus x squared. Oh! Oh! Well, that's not bad. Doesn't everything cancel?
Almost.
Like all that stuff cancels.
Nice.
All right, so now we just have a constant on the inside.
Reverse chain.
No reverse chain rule. There's no variable.
I tried.
Oh my goodness.
Right? This all just simplifies to 5 halves. So what does the 5 halves is a constant. That's going to factor out to the front. And then we have integral 1 to 4 dx. What does that turn into?
4 minus 1.
It's
4 minus 1. The length of the interval. 3. So this should be what you should be able to write down as the next step. 2 pi times 5 halves times 3. So if you're integrating a differential, you get the length of the integral. Length of the interval. Jordan, question?
Where did the 5 halves come from?
5 halves came from, so all these variable terms cancel and then the square root of 25 fourths.
Oh.
Because we still have that big root on the outside that will take the square root of 25 fourths. So our final answer is a nice round number of pies, 15 pi. Oh. Sometimes the answer looks nice. Other times it looks untouchable.
Considering how crazy it was getting there.
I know. This is not what we expected, was it?
No.
No.
15.
Math is not what it seems. All right, so let's go ahead and stop there. I will see you all on Wednesday. Good luck jamming on the homework. And remember, if you have questions, use this collaborative space up here. Put some stuff up there. Anything you want in there, and I will get back to you. Roberto, question? Oh, let me stop. Thanks for letting me know how that all went.
Yeah. It's very useful now. I was able to use it for my